Let's start off with this this system of differential equations, nonlinear. Dx dt is going to be x times x minus 5. And dy dt is going to be y times 6 minus 1. Great. And let's find the nullclines. So we're going to set each of these separately equal to 0 and see what we get. So setting this one equal to 0, well, we're either going to get x equal to 0 or x minus 5 equal to 0, which becomes x equal to 5. So we actually have two nullclines here. One is x equal to 0, one is x equal to 5. And I should say these are two, so you can either call them x nullclines, like he was calling them in class, or if you look at problem, I think 5 on your problem 6 on your homework, they call the x nullclines the vertical nullclines. Not because they're vertical lines, although they are in this problem, in future problems they will not be, because the arrows on those nullclines point vertically. So I want to be very, very specific. A vertical nullcline is a nullcline where all the direction vectors point vertically. A horizontal nullcline is a nullcline where all the arrows on it point horizontally. And that makes sense because what you're saying here is that dx dt, right, the change in x is 0. If the change in x is 0, there's no left or right, it's all up or down. So let's start graphing this. So my vertical nullclines are going to be x equal to 0, which is the y-axis. And normally when we draw lines, we put like arrows at the end. We don't usually do that for these because we have direction field arrows that are going to be like maybe different than the arrows. So don't put arrows at the ends of your line, which I know is kind of weird. And we're also going to get x equal to 5 over here. So there's x equals 0, there's x equals 5. I haven't drawn the horizontal axis because it's going to be one of my other nullclines. So setting the other one equal to 0, we're going to get y equal to 0 or y equal to 6. So here's y equal to 0. Here's y equal to 6. Okay. And something to make note of, wherever different types of nullclines cross, you have an equilibrium. So here's an equilibrium at 0, 6, right? Because this is equal to 0 when y is 6, and this is equal to 0 when x is 0. Here's an equilibrium at 5, 6. Here's an equilibrium at 0, 0. And here's an equilibrium at 5, 0. It makes sense that you get equilibria where the nullclines cross because you're just finding the points where both dx dt is equal to 0 and dy dt is equal to 0. That point right there is where both are true at the same time. So any point where an x nullcline and a y nullcline cross is an equilibrium point. Or any point where, I don't know what's that. So let's go ahead and start talking about classifying them. So to classify them, or I really should say to graphically classify them, we need to draw the arrows like he was doing in classes. So what we're going to do is we're going to pick a point that's not on any of our nullclines. Or especially not, I mean, you can pick a nullcline, but it's usually best to pick something like active. So let's pick the point 1, 1. If I pick the point 1, 1, dx dt is going to be 1 times negative 5 from 4, which is going to be negative. So at 1, 1, we're going to be going down. And at 1, 1, dy dt is going to be 1 times 6 minus 1, which is 5. We're going to be oh, sorry, I messed that one up. Dx dt is not about up or down. Dx dt is about left and right. So at the point 1, 1, dx dt is equal to 1 times negative 4, which is negative 4. So we're going at the point, let's say, let's be a little bit more clear here. Let's go 1, 2, 3, 4, sure. Right, okay. So at the point 1, 1, I picked the point 1 because it's easy, yes, and because it's not on any of my nullclines. So we really just pick like any point. It's not on a nullcline. That's easy to plug in. And then at 1, 1, the dy dt is going to equal 1 times 6 minus 1, which is 5. So I know that the point 1, 1, we're going to be going left and up because dx dt is negative and dy dt is positive. So now here's the thing. So here I'm going left. And the thing is that until you cross one of the nullclines, specifically one of the x nullclines, you don't change your left or rightness. So, right, this is where dx dt is equal to 0, and this is where dx dt is equal to 0. In here, it's never equal to 0, so it's either always positive or always negative. Since we found it to be negative here, it's always negative. But then on the other side here, it's going to change sign. And typically, whenever you cross a nullcline of the type that you're thinking about, you're going to change the direction. So if I cross an x nullcline, I change from being left to being to the right. And the same deal over here. I cross this nullcline, I'm going to change from going to the left to going to the right. In fact, these are the only determinations. So I know that I can do, right, I'm going to be looking like this. Now the problem with this is it's kind of a pain to write out. Right? And it would be true up here, right? So crossing this green nullcline doesn't affect the left or rightness. I'm going to erase these equations. These equations are kind of a mess. We can write them up again if we need to. Okay. And then to the right. Okay. And then all these are going to the left. Okay. And then we also said that at 1, 1, dy dt is positive, so we're going to be going up. So right here, we're going to be going up, 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 up. And then when we cross this, we're going to change the up direction to down. So everywhere in here, we're going to be up. And it's kind of, right, you can see how this is kind of a giant pain, but which is why people don't usually draw so many arrows. Yes, Kat, I know you would like to leave. And then up here, we've crossed a y nullcline, so we change from going up to going down. This is an x nullcline, it doesn't change the up or downness. So if you cross a nullcline, the arrow will change. Well, it depends. So someone asked me if you cross. So if you cross the nullcline of the type you're talking about. So I'm talking about the up or down direction. If I cross a y nullcline, I'm going to change from up to down or down to up. On the other hand, left, right, if I cross an x nullcline, I'm going to change from going to left to going to the right. Okay, and then, oh, I forgot about down here. Ugh. Ugh. And so down here, it's still the same x stuff. But now down here, we'll be going downwards. All right, there we go. So let's take a look. So let's start at this point here. 0, 6, well, if I start up here, I'm going left and down. I'm going towards that. I'm starting here, I'm going up and left. I'm going, right. It looks like no matter where I start, I'm going to be going inwards towards my equilibrium, meaning it's probably going to be a stable node. So it looks like 0, 6 is a stable node. Because all the right, no matter where you start, if you start here, I'm going to go right and left. I'm probably going to go, or sorry, right and down. Or if I start here, I'm going to go, like that. It could also maybe be a spiral, and that's kind of That's kind of the hard part to usually tell when you've got either stability or instability, if it's a stable spiral or a stable node versus if it's an unstable spiral or unstable node, right? Like, it's hard to kind of tell whether your stability is node or spiral or your instability is node or spiral. Let's take a look over here as well. So here we kind of got the opposite thing happening. Here, everything's pointing away, right? If you start up here, you're going right and up, you're going away, you're going away, you're going away, you're going away. So this looks like an unstable node. And that's at the point of 5, 0. And then these ones, well, this one here looks like kind of like a saddle, right? Because I'm going in towards it, but I'm going up away from it. So I'm kind of going like that and like that. Or down below, I'm going in towards it, but down. So like that and like that. And the same kind of thing is happening up here as well, right? Here I'm going in towards it, but out to the left. Here I'm going towards it, but out to the right. Here I'm going towards it, but out to the left, towards it, but out to the right. So it looks like we have a saddle at both, let's see, what do we got here? 5, 6, and 0, 0. So now what I would like to do is to actually look at the system of differential equations and find the Jacobian to see if we were correct in our assertions. So let me remind you of our equations, which I have lost on my, let's see, where'd you go? There we go. So our equations were dx dt equal to x times x minus 5, which is x squared minus 5x. dy dt was y times 6 minus y, which is 6y minus y squared. Really, the Jacobian, partial of this with respect to x is going to be 2x minus 5. Partial of this with respect to y is going to be 0. Partial of this with respect to x is going to be 0. Partial of this with respect to y is going to be 6 minus 2. Great, so let's plug in all the points. So if we plug in, I feel like it does look a little bit dark. Let me turn off the lights a little bit. Maybe that makes it a little bit easier to see what's happening. So the Jacobian at 0, 0 is going to be -5, 0, 0, 6. The nice thing about this example is it's super easy to see the eigenvalues. Right? The eigenvalues are -5 and 6. Oh, we have a saddle. Because the eigenvalues are opposite sides. Right? They're both real and one's positive, one's negative. Let's look at 0, 5. Well, if I plug in 0 for x and 5 for y, it was 0, 5, right? No, it was 0, 6, excuse me. Plugging in 0, 6, we're going to get, let's see, so -5, 0, 0, and 6 minus 12 is -6. Oh, that's a stable node. If we plug in 5, 0, we get 10 minus 5, 0, 0, 6 minus 0. Oh, it's an unstable node. We plug in, what was our last one? Let's see, 5, 6, I think. We're going to get 10 minus 5 is 5. 6 minus 12 is -6. So again, here we get a saddle. So we were right? Our graphical interpretation was correct. And if you like, let me just show you real quick. Look at Desmos here. Not Desmos, p-planes, all right. It's been a while since we've Desmos. So here is the equation. I've got lots of stuff up here. Here's a picture of what I was just doing. But if we graph the face plane here, oh yeah, it's already there. It's already graphed. Also, you can totally, if we want to look at, we can look at the nullclines. So those are the nullclines. And I graphed them with the arrows. So they're showing, oh yeah, those vertical nullclines are actually, those vertical lines happen to be vertical nullclines because the arrows on them all point straight up. So I didn't actually draw them, right? Like on this nullcline here, we would have straight up like that. Yeah. Something weird. Well, let's go graph this again. Let's actually go to the regular nullclines. So then if you start picking points, you can see like if you start here, oh yeah, you're gonna go to, I don't want the whole thing there. I don't want that. Right, so you're just gonna like, right, there's our stable node. So if we start close to it, we're gonna end up out. But then if we start like, right, if we start over here, oh, then we're just gonna get pushed away. Right, so here's our unstable node. We get way pushed away from that. And here are our saddle points. Oh yeah, we're going way off down that way. So basically, if we start anywhere like up here, like in this region, we'll end up getting pushed towards our stable node. If we start anywhere down here or over here on the right, we'll go off, we'll diverge, right? We'll go off into infinity in some way or the other. Kind of interesting. Let me stop sharing. So that's kind of the whole idea, right? Is that we want to use the nullclines to help us determine what kind of stability we have at our various steady states. Let's look at a slightly more complicated example. I wish my green pen was hanging in there. I guess I could use orange. The problem is I feel like it's hard to differentiate very easily between the orange and the red, but maybe that's just me. Also, what you can say, right, like in this region up here, you could say that, okay, over here, X is increasing and Y is decreasing because you're going to the right and you're going down. Or over here, X is increasing and Y is increasing. We're specifically saying this kind of to lead towards, I know you have the robin and the worm question, where you're asked like to look at the different areas that you're segmented into and to talk about like if their population is growing or decreasing. And it's basically just based on which way your arrows are going, right? If your arrows are going to the right, that variable that's on the x-axis is increasing. If your arrows are going to the left, that variable is decreasing. If your arrows are going up, the y-axis variable is increasing. If your arrows are going down, your y-axis variables are decreasing. So let's look at another example. Where's my number? Sorry, I had things numbered in this. Oh, I see. Sure. Yeah. Let's look at this one. Let's say I've got in red dx dt equal to 2x minus x squared minus xy. And in orange, dy dt equal to, can you guys see the orange all right? That doesn't look too bad. Equal to xy minus y. Okay. Again, let's find the nullclines. So we're going to find the nullclines. We're setting each thing equal to 0. So let's see here. Typically, what you are trying to do when you're finding nullclines is you often want to factor as much as possible. So I'm going to factor out an x from here. So I see that I have x times 2 minus x minus y equal to 0. And here I have y times x minus 1. So I have a few nullclines. My vertical or x nullclines are going to be where x is equal to 0, or where 2 minus x minus y equals 0, which I might reimagine as x plus y equal to 2. My horizontal nullclines, or my y nullclines, are going to be where this is equal to 0. So either, basically you're taking either factor and setting it equal to 0. So either y equal to 0 or x minus 1 equal to 0, which is x equal to 1. Okay. So let's draw things. So x equal to 0 is the vertical axis. Y equal to 0 is the horizontal axis. So here's my, do I have enough room? Yeah, I'll try and make this be enough room. Let me see. Yeah. So here's my, wow, that's not a very good vertical line. Let's try that again. So here's x equal to 0. And then we're also going to have y equal to 0. And then we're going to have what? X plus y equal to 2. So that's going to have an x-intercept of 2 and a y-intercept of 2. Go up 1, 2 over 1. And then I also have x equal to 1 as a y multiplying. Okay, so here's what we know. We know that on these red nullclines, all of the arrows are going to point vertically. They're going to point up or down. Because on those red nullclines, dx dt is 0. There's no change in x. On these orange nullclines, dy dt is equal to 0, meaning there's no change in y, meaning all of our arrows are going to point horizontally. So let's go ahead and let's pick up, so you can actually pick a point on a nullcline. What you can't do is pick a point at an equilibrium because they'll both be 0. So let's pick a point over here like -1, 0. I pick this point, -1, 0. Well, let's see. So if I plug in, so I know that dy dt is going to be 0 already. Let's figure out what dx dt is. So I pick -1 for x and 0 for y. I get -1 times 2 minus 1 minus 0. So I get -1 times 2 plus 1, which is -3. Meaning my dx dt here is negative, so I'm pointing to the left. And that's going to be true. I was going to use red. Sorry. It's kind of hard. Well, actually, really, I mean, it doesn't really matter which color. I suppose I should use a different color. So here I'm pointing to the left. And not up or down. But then when I cross this x nullcline, I'm going to change my left or right direction. So I'm going to change from going left to going right. And then here is an equilibrium where the different types of nullclines cross. So I don't point in any direction at that point. And then when I cross this x nullcline again, I'm going to be pointing to the right. Okay. And then also on this orange nullcline, again, I'm purely horizontal. So down here, I keep pointing to the right, And up here, I'm going to cross an x nullcline. So I'm going to change the direction I'm pointing. Right. On the other hand, on these red nullclines, my arrow should be totally vertical because dx dt is equal to 0. So if I pick a point up here like 0, 3, if x is 0 and y is 3, well, this is going to be 0 if x is 0. If x is 0 and y is 3, you get 3 times -1, which is -3. So up here is 0, 3, I'm pointing downwards. And I'm going to keep pointing downwards until I cross a y nullcline. So it's still downwards here. And that's not an equilibrium where the same type of nullcline crosses itself. You don't get an equilibrium. You only get an equilibrium where the different types of nullclines cross each other. Let's keep going. So down. But now I'm going to cross a y nullcline and be pointing up. And then along this, the same thing is true. So right, I'm pointing down, 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 down. And then I cross a y nullcline, I point up. Then I cross another y nullcline, I point down. So often the pictures people make are just with the arrows on the nullclines, because then you can kind of figure out what's happening in each section. So basically what this means is that everything up here is pointing down. So we're down, down, down. Right? And then everything up here has to be pointing up. Everything down here has to be pointing down. And everything over here has to be pointing up. And then left or right. So everything up here, which I have to be a little extra careful here. Sorry, yeah. So everything up here is pointing left. But then on the other side here, we're gonna be, no, that's good. We're good. Then over here, we have to change the direction, right? Because we've crossed the next null line. So over here, we're pointing to the right. And then down here, we're gonna be pointing to the left. As we cross another X null line. Down here, we're still pointing to the left. Over here, we're going to be pointing to the right. Over here, we're going to be pointing to the left. Over here, we're going to be pointing to the left. Okay, I think you get the idea. Whew, all right. So hopefully you guys can see that okay. Let's talk about our equilibrium. So first of all, where do we have equilibrium? Well, I have an equilibrium here, here, and here. So it looks like I have an equilibrium at 0, 0 for sure. I also seem to have an equilibrium at 1, 0. Sorry, not 1, 0. Yeah, at maybe 2, 0, I think that is. So how would we figure that out? Well, so I'm not even sure. No, it's fine. Yeah. So we could set the equations equal to each other, right? We can figure, right, not really equal to each other, but like what we usually do. So I know that x could be 0 and y could be 0, or x could be 0 and x could be 1. That doesn't work if x is 0 and x is 1. Or y could be 0 and this could be 0. So y could be 0 and 2 minus x minus 0 could be 0. So x could be 2. So 2, 0. Yep, that's a point there. And then you could also have where these are both true. So x could be 1 and 2 minus x minus y could be 0. So 2 minus 1 minus y could be 0. So y would have to be 1. So you get the point 1, 1, 2, 0, and 0, 0. All right, let's see if we can figure out what's going on. So just looking at what's happening at 0, 0, I've got things pointing in this way and out that way. What do you think we have? I would say we probably have a saddle. I'm moving my cat. She's okay. She's still here. So definitely 0, 0. I think we have a saddle. Because again, right, we're kind of coming in this way, but then we're getting pushed out that way. So things are doing, right, we're going down and to the left. We're going up and to the left. We're going down and to the right. We're going up and to the right. Okay. But then these other ones are a little bit more challenging. So, right, if you look, say, over here, at this point here, you're kind of, so here you're going up and to the left. You're kind of going that way. Here you're going left and down. Here you're going down and right. Here you're going right and up. So it could be a spiral, but it could also be right. So I really I'm not good at telling. I think it's stable because it kind of looks like we're pointing kind of in towards this point, but it's not super clear. So if I had to guess, I would guess 1, 1. I would just guess it's stable. It's either a stable spiral or a stable node, I think. Let's look at this other one here. This 2, 0 point where, so now we're going up and to the right. Sorry, up and left, apologies. And over here, we're going down and left. So we're, sorry, yeah, down. So we're kind of going that way. And then when you cross this, you're supposed to be going wholly down. And then, so I'm kind of looking at this like it might also be saddle. Right, because you're kind of going down this way, kind of going up this way. Let's take a look and see. Yeah. So let's find our Jacobian. So again, Brett, maybe there's something I'm not seeing that about the graphical method that like supposed to be super easy. I don't find it really easy to like start at a point and be like, okay, I think I know what happens. Let's go ahead and yeah, let's find our stuff. So yeah, okay. I think I'm mostly right about what I said. So let's see here. So our Jacobian, our partial with respect to x is 2 minus 2x minus y. Partial with respect to y is negative x. Partial with respect to x is y. Partial with respect to y is x minus 1. Right? Just as to remember that this is our function f, this is our function g, and your Jacobian is partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. That's Jacobian. All right, so let's go to Jacobian. We're pretty sure we know 0, 0 is a saddle. Let's double check. At 0, 0, we get 2 minus 0 minus 0, 0, 0, negative 1. Yep, definitely a saddle. Look at those opposite sign eigenvalues. All right, let's look at 2, 0. That's going to be 2 minus 4 minus 0. So that's going to be 2 minus 4, so negative 2. And then 0, negative 2. And then 0. And then 2 minus 1 is 1. Also a saddle, opposite sign eigenvalues. One nice thing about a lot of these examples is a lot of these examples have 2 by 2 matrices where you have a 0 here or a 0 here. So it's super duper easy to see what the eigenvalues are. And then let's do the last one. At 1, 1, we have 2 minus 2 minus 1, minus 2, minus 1, 1, and minus 1, 0. Okay, so this one we cannot automatically read the eigenvalues. We actually have to do some work. Did I do this work? I feel like I did this work in my notes, but I'm not seeing it, which is, oh, I did it over here. Cool. All right, yeah. So my trace is negative 1. So we know that it could either be a stable node, a stable spiral, or it could be a saddle still. But if your trace is negative, it's either stable or a saddle. And then my determinant is 0 minus negative 1 times 1, which is going to be 1, which is positive, meaning I'm in either saddle land, sorry, not saddle land. I'm not in saddle land. I'm either in node land or spiral land. So I either have a stable spiral or a stable node. That seems reasonable, but it definitely looks more spirally, right? Because you've got kind of this behavior. Just to kind of draw a little bit more clearly here. So just to watch you. So my eigenvalues would be negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 all over 2. Oh, that's going to be complex. So we have a stable spiral. If you look at this picture here, so if you look specifically, right, at the point, so this is 1, 1. If you look at that point right there, so over here the arrows are going down to the right. Over here the arrows are going. So we go down to the right. We have to cross this going horizontally. Then we're going up and to the right. So we have to cross. But we have to cross this. So I think the rationale here, the y is the spiral, is because we get to this kind of quickly, and so then we have to be going straight up. And then it kind of takes a long while to get here. But when we get here, we have to be going horizontally and then straight down. And then, right, so it looks spiral. But again, I'm not great at justifying this argument, right? I feel like there could be pieces I'm not, now I know it's a spiral because I did the math, but just looking at the graph, I think it's kind of difficult to see. Right, because I think if you had just looked at the graph, you might have been able to argue that that was a stable node instead of a stable spiral. I wonder if one of these has an unstable spiral. That would be good to see as well. No, that one does not. Yeah, I should have picked one with an unstable spiral here. Sorry, let's go. So let's I think we can fit in one more example here. Actually, let me see. No, I think we're good. What I should point out, so looking at p-plane real quickly here. Let me show a screen. So if we look at the equations that I just erased, which are, all right, where'd you go? 2x minus x squared minus xy, and x minus y minus 2. Graph those. So there's our phase plane. Did I make a mistake here? Because I feel like I'm missing a null line. Oh yeah, sorry, it's xy. Yeah, I mixed up two equations. Sorry, it should be xy minus y. There we go. There we go. There's the x. So if you look, right, like, so again, right, we said, I erased it already. Right. So, right, we said saddle, also saddle, stable spiral. So if you start like kind of right near your saddle here, you're going to saddle away, which is definitely a thing people say. But then, right, if you start over here, right, you still get pushed in a direction where you end up getting spiraled into your stable spiral. Here we're saddling. But like if we start right here, oh, we saddle away. But then if we start like up here, whoa, that's funky. So, right, that's the trajectory that goes along this way. So again, right, things locally act like kind of what they're supposed to, but when you get away from kind of any of your equilibria, weird things happen. Yeah. Okay, let's look at another example. I'm gonna try and modify this one just a little bit to be like your worms and your ravens. It's not gonna be super realistic, that's all right. So let's say the rate of change of the worm population is negative r squared plus w minus 1, which might be semi-realistic in that, right, the more ravens there are, the less worms there would be. The more worms there are, the more worms there are. So this actually seems like not a terrible equation. And let's say that the raven equation is going to be dr dt equal to, what do I got here? R times 3 minus w minus r. Which may or may not be realistic. I don't really care how realistic it is. So let's go ahead and draw the nullclines. And then we're going to talk about, well, we'll talk about the stability, we'll also talk about the growth, meaning in each section. So where the nullclines, the different types of nullclines kind of cross each other, that kind of, let's just draw it and I'll say the words. So saying this one equal to 0, and again, we're thinking of w as our x variable and r as our y variable. We've got, I'm going to solve for w here. I've got w equal to r squared plus 1, which I'm thinking of as x equal to y squared plus 1. I feel like I've made a mistake here. No, that's right. The mistake I made was writing the wrong thing here. Sorry. I meant for this to be good. We can just go with this. This will be fine. Okay. And this is going to be Sure. Let's see, we're going to get either r equal to 0 or 3 minus w minus r equal to 0. So r plus w equals 3. All right, so let's go ahead and graph these things. Hopefully the graphs don't turn out to be too terrible. I think they're fine. Yeah, they're fine. All right, notably, the origin is not going to be in equilibrium here, which is atypical. Right? Most of the time we do these problems, the origin is in equilibrium. It's not for these particular equations. So let's see. So again, r is my y, w is my x. So this is like y equal to 0. This is like y plus x equals 3, or y equals 3 minus x. Okay. So y equal to 0 is the horizontal axis. And then my vertical axis is not a nullcline for once. So here's my vertical axis. All right. And I guess I should really say, right, this is really not y equal to 0. This is r equal to 0. And then we also have y equal to 3 minus x. So I'm going to go up 3 over 3. And y equal to 3 minus x, right, has a y-intercept of 3 and an x-intercept of 3. Okay. And then my red nullcline is x equals y squared plus 1. So that's going to be a rightward opening parabola. And let's see if I just, yeah. And I already know they're going to intersect at the point 2, 1. Oh, I want to use red. Sorry. Okay. So we've got a couple equilibria. Three to be exact, it looks like. So there's definitely an equilibrium at the point 1, 0. I don't want to write those in though. Let's just write them. Let's continue. So our equilibrium appear to be at the point 1, 0. And I'll just tell you for the sake of time, this equilibrium here is the point 1, 2. Sorry, 2, 1. Right? If my, right, this is my W axis, this is my R axis. Yeah. So, right, if W is 2, R is 1, right? W is 2, R is 1, check. W is 2, R is 1, check. And then there's also another point down here, which I believe is the point where I think R is -2, and I think W is 5. Right? Yep. 5 plus -2 is 3, and -2 squared plus 1 is equal to 5. Check. So those are equilibria. You can totally find them by setting things equal to each other, but I want to use these last 4 minutes to kind of tackle this. So again, let's figure out what's going on. So we have kind of, yeah, we have a bunch of little sections here, right? So you can kind of think of like, this is a section, this is a section, this is a section, this is a section, this is, right? Every nullcline you cross is going to change a direction. So let's just pick a point like 0, 1 and see what's happening. So if W equals 0 and R equals 1, then dW dt is going to be -1 plus 0 minus 1. So it's going to be -2. So the change in the x direction or the W direction is going to be negative. So we're going to be going left. And the change in the R direction or the Y direction at 0, 1 is going to be, well, let's see. W is 0, R is 1. So 1 times 3 minus 1 minus 0. So it's 1 times 2, which is the positive. So we're going to be going up. Great. So right here, you could say, okay, yeah, now I got my colors backwards. Sorry. So right here in this quadrant or this region, you could say that the population of ravens is growing and the population of worms is decreasing. Because worms are the horizontal W axis, right? And we're going to the left that way. And ravens are the vertical axis, go that way. And then, so then if we cross this orange nullcline, your up down this changes. So over here we are down, but still to the left. And then if we cross this red nullcline, we're going to change from being left to being right, but still down. And then if we cross this orange nullcline, we're going to be up, but still right. If we cross this orange nullcline here, we're going to be down, but still right. If we cross this orange nullcline again here, we're going to be up, but still right. And if we cross this red nullcline here, we're going to be from down right, we're going to be down left. And I think we still got this little section over here. If we cross this one, we're going to be changing our up downness, so we're going to be left, down, and up. Kind of funky. All right, so let's ask ourselves right here, what's our stability look like? To me, it looks like it's definitely a saddle, because we're going, oh no, it's not. I don't think it's a saddle. I think it's actually an unstable node, right? Because we're going both away from it in that direction and away from it in that direction. So my guess is that 1, 0 is an unstable node. This point here, 1, 1. It's hard to tell. And so we're going down and left, and then we're we're going down and left, and then we're supposed to be going up and left. I guess it might be a saddle there, right? Or if we start here, right, we're going down and right. Right? It definitely feels saddly there. And then over here, we're going up and right. We're going left and up. This feels like it could be a stable spiral, but I don't really know. Let's look at p-plane. I know we're out of time. Let's look real quick, and then I gotta go. Let's go ahead and look at p-plane just to kind of see. So again, I think p-plane is a very useful tool. Let's take a look at this one. So I've got, let's see, dx dt is negative y squared plus x minus 1. And y dt is y times 3 minus x minus y. Graph this thing here. So let's see. So I said this looked like an unstable node, and that appears to be what we have, right? We're definitely shooting out away from it. Okay. And then I said this appeared to be a saddle. I think that looks pretty saddly, yeah. And then this I wasn't really sure about. Oh, this is also looking like a saddle here. Yeah, it's looking saddly. So a couple saddles and an unstable node. Interesting. And yeah, I guess you could kind of talk about this one being saddle, because again, right, you're going with this one, you are going towards the equilibrium in one direction. Really, I feel like that, to me, that feels not super saddle. Like, yeah, I guess that's a saddle, but sure, okay, right. So here, I guess here, I get it. So you're going up and to the left, but then you cross this vertical nullcline and you start, so right, I see, okay. Let me do this one more time here. So here you're going up and left, and then you cross this and you start going down and left. Okay, that makes a little more sense. Or over here, you're going down and right, but then you cross this and you're going up and right. or you're going down and right, and then you cross this and you're going down and left.